function, and that was the minimum energy required for an electron to be emitted from a piece of metal, from the surface of a metal. Okay? Then we started to look at this equation. In this equation, here, that's on your data sheet, E is the energy of the photon. And how do you get the energy of the photon? With any one of these two equations, also on your data sheet. Then this thing on the right-hand side is has to do with the energy of the electrons on the metal. Electrons on the metal. Okay, so the thing on the left-hand side has to do with the wave. The thing on the right-hand side has to do with the energy of the metal. The electrons on the metal and their energy. Okay, now energy is measured in joules, right? And work is also measured in joules. So we are comparing the same things with one another. We're comparing joules with joules. Joules. Right? So if the light that comes in, the photons that comes in, have just enough energy, then it is the same as the work function. So if the energy of the photon is exactly the same, the minimum energy for the electron to be emitted is the same as the work function. If there's more than enough energy, remember I said I drink my coffee? If I get more than enough coffee, then I just move faster. Then if the energy is more than the work function, then they move faster. Then they have extra kinetic energy. Okay, so EK is kinetic energy, you know that. So if this energy is equal to the work function, then they will just start to jump. Any extra energy will be equal to the kinetic energy. What is this again? This is the energy of the photons coming in. So the energy is equal to Planck's constant times the frequency of the light coming in. Okay? Then what is this again? This is the work function we did here, the work function. What is that? It's the minimum energy required. That is equal to Planck's constant times the threshold frequency. Remember threshold frequency we did on page 1. We spoke about the threshold frequency. What is that? The minimum frequency of the light needed to emit electrons. So the minimum energy is linked to the minimum frequency because the normal energy is equal to the normal frequency. Okay, right. Then we had Planck and Einstein, and they brought these two concepts together, and from that we saw that, you know what, light, the electromagnetic spectrum, is a wave, but it's also a particle, and that was like mind-blowing for the science world, and they're still busy developing that. Okay, right, let's look at calculations. It says there, the frequency of light photons is that. It shines on nickel, which has a work function of that. Calculate the kinetic energy of an emitted electron. So they tell you, there is a piece of metal that is nickel, and it has a work function of 8 times 10 to the power minus 19 joules. And they say they shine a light on there that has a frequency of 1.6 times 10 to the power of 15 hertz. Okay, and now they say an electron is emitted, and they want to know what will be the kinetic energy of that electron. Okay, so info table. Right, let me first start with the formula. Formula is E is equal to the work function plus kinetic energy. Okay, so we have F, check. We have W, check. The question was the kinetic energy. Okay, so that's the question. We have the work function, but they didn't give us the energy. They gave us just the frequency. We can calculate it because there's a formula, E is F times frequency. Okay, and where do you find H? H is Planck's constant. on your data sheet. Okay, so we have 6.63 times 10 to the power negative 34. What is that? That is Planck's constant. Times the frequency is 1.6 times 10 to the power 15. The work function was given, plus kinetic energy. Okay, so doesn't your notes aren't here? Are you on your calculator for us? What do you get? You must minus, right? Mm-hmm. Sure, send them down. 2.6. Yes. 2.61 times 10 to the power negative 19 joules. Yes. Okay. Now, this is a very small value, but this is the energy of one electron. Okay. So they can tell you, all right, now we see that there is 1 million electrons being transferred. What is the total energy? Then you must multiply by 1 million. Okay. Now you see I left a bit of space open. Now I'm going to ask, what is the velocity of one of these electrons? What is the velocity of one of these electrons? How are you going to do that? What did we just calculate? And can you go from kinetic energy to velocity? Yes. Okay, with this formula. Now kinetic energy is a half mv squared. Ooh, mass. We need mass.
The mass of an electron.
That's the charge. Charge of an electron. The mass of an electron is on your data sheet. 9.11. Okay. So they love to ask this question, so you must know where to find these values. We've just calculated the kinetic energy, a half, and the mass, like I said, is on your data sheet. V squared, and Sinomta, are you on it?
Yes,
we will be waiting. Remember to square root. No. Yes. Shift setup 7.5. Shift setup 7.5. 7.5.
Oh, this is 7.5551 times 10 to the power 5.
7.56.
Yeah.
Times 10 to the power of 5, and new unit?
Meters per second.
Meters per second. That is super fast. Do you see that? Okay. Right, now. You should have asked yourself, ma'am, but so every time the sun that has UV rays on shines on a piece of metal, does it emit electrons? Not always. Okay? First of all, what's the difference between metals and materials like your book, your clothing, and? Okay, let's read. First of all, materials. Materials are like rubber, clothing, wood, something like that. As light strikes a material, photon energy is transferred to the electrons. So photon energy transferred to the electrons of the material. The amount of energy transferred depends on the material. Okay? When the frequency of light differs from the natural frequency of the electrons, light is transmitted or scattered, and no or very little energy transfer occurs. Okay? When frequencies of similar light shines on there, the light is absorbed and the greatest energy transfer occurs. So that just means, and you've experienced this, some objects, when light shines on it, it doesn't get warm. Yes? And some objects, it does. And that depends on the object. Okay. So that's materials. There's not a lot of like electrons being jumped or anything like that. Now when we go to metals. When light strikes a metal, photon energy is absorbed by the electrons, which move them from their ground state to a higher energy level. Okay, now, I think you should remember from grade 11 that we said electrons can jump to a higher energy level. Remember we quickly discussed that they can jump from 2s to 2s to 2p or 3p to 3d or something like that. Okay, so electrons can jump. So when metals get energy, the electrons jump to a higher energy state. Right. Then the electrons drop back to their ground state, to where they normally are, and release the absorbed energy as light with the same frequency as the incident light, the light that comes in, giving the metal a shiny appearance and luster. So that is why metals start to glow when they get warm. Is what happens, light shines on here, the electrons absorb the energy from the light, and they jump to a higher energy level. Then they immediately drop back again because they are unpaired, orbitals are open, blah, blah, blah. So they're unstable, so they drop down back. When they drop down back, they release that energy that they got. It's almost like they get it, they go back, they pass it on again. Okay? And when they release that energy again, that's what causes the metal to become shiny. Okay? Now, this here is the photoelectric effect. If the frequency of light is high enough for the particular metal, okay, so when they get not just energy to go to a higher energy level, but sufficient energy to, they jump off the metal. So when they get high enough frequency of light, then electrons are ejected from the metal. Electrons are ejected from the metal. And that is the photoelectric effect. So here, I'll show this to you. Here energy comes in, and then they jump to a higher energy level. And then they drop back down again, and they release that energy again. So when they get energy of blue light, they jump up, and then when they jump back down, they release blue light again. Up and down, up and down, up and down the whole time. But when they get high enough energy, then they're not only going to jump up, they're going to jump off the piece of metal completely. Okay? So you don't always get electrons ejected, it must be sufficient frequency. Okay, and that is when you get the absorption and emission spectra. Okay, what is the absorption spectra? For electrons to move to a higher energy level, excited state, they must absorb a quantum of energy. Okay, so they must absorb that energy. So how do we get this absorption spectra? Have you seen that sometimes before in your life? How do you get this absorption spectra? That is when you have cold gases and you shine light through that cold gas. So when you shine light through that cold gas, then the light photons are absorbed by the gas. So you have cold gas, you shine light through it. That cold gas is going to absorb any heat that it can take. But it's going to absorb only the frequencies that resonate with the particles. Okay? So, like if you throw a lot of coffee my way, I'm only going to take the coffee that I want. Are you with me? Okay, so the gas only takes the nitrogen, oxygen, whatever's in that gas, only takes the energy that resonates, that has the correct frequency that the particles need. Okay, and then those electrons move to a higher, from a low to a higher energy level. And that is when, so this was the light that you shine through the cold gas. And then when you look at the light from this side through a prism, you see, but wait a minute, some of these parts of the light is gone. Where is it? It was absorbed by the gas. So then we know, okay, this gas absorbed a piece of red, a piece of orange, a piece of yellow, a piece of green, blah, 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 blah. Okay, so this gas absorbed these frequencies. So it means in this gas, there must be nitrogen, because nitrogen absorbs blue. There must be helium, because helium, because helium absorbs yellow. Okay, so that is how when they look at gases in from different planets or in the universe or wherever, they send it through a prism and they say, oh, this is gone, this is gone, this is gone. There must be nitrogen on that planet or wherever. Okay, and then what they also can do is they can take this gas and they can make it hot. What do hot things do? They give off, right? So they take this hot gas and they let the light that this hot gas releases, look at it through a prism, and then they see, oh, this hot gas releases this bar of light, this bar of light, there must be nitrogen in there. There must be helium in there. So there's two ways to identify these elements, either through cold gas or through hot gas. Cold gas gives you the absorption spectrum because cold absorbs. Hot gas gives you the emit, release, exit, emission spectrum. Okay. Now, they don't ask a lot here. These that I've written down here, this is what they ask. Cold gas, warm gas. Do they go from a lower energy level to a higher energy level, or a higher energy level to a lower energy level? Okay, so that is what they ask there. Now, this here is a spectrum tube. Okay, so this, I just want you to see, this was stationary here. Did you see? It's stationary. Quickly come on. Okay. This was stationary. And I moved it. There's just a needle sticking out and then black and white paper. Okay, it was stationary. If we put it in sunlight, then it's going to start to rotate. Do you see that? Photoelectric effect. Sunlight on the piece of white causes the electrons to jump, and then the momentum of the electrons causes the thing to turn. And this will continue to turn, and at night when it stops, it will stop. And light continues. Okay. This here is a spectrum tube. So this shows that it gives very high voltage. There's gases and a piece of metals in here, and then it sends electricity through it, and it causes the gas whatever to heat up, and then it emits emission spectrum. It emits the color, the frequency. Now this is hydrogen. What color do you think hydrogen?
Yellow.
Yellow is helium, so
Nitrogen is blue. Oh yeah.
purple. Purple.
Pink. Okay.
It's purple. Pink, yeah.
So there's hydrogen gas, and so now that's alright. They can measure this frequency with specific light, camera, blah, blah, blah. They can say, oh, okay, so you know hydrogen is this color, this frequency. So if they get the same color from a different sun or planet or a star or whatever, they say we know that star has hydrogen. Alright? What color do you think is Mercury? Okay, so Mercury is a metal, right? Do you see this small piece of metal there?
No.
Hey. Oh.
Oh, yeah. No.
Light
Like,
blue.
look at that where it's concentrated.
It's blue.
Like a very light, bright blue.
It's
Yeah.
purple.
Yeah.
That's a hot.
Purplish,
Is it gonna be hot?
no, it's not hot, but I don't want to touch it while it's on because this will shock me.
What is this?
See you tomorrow. This is neon.
Wow. Yeah, that's nice. Yeah.
Alright, you can see so it gives off rays. Okay, so every element has its own frequency.
You.
So, but not like some is red, some is more red, some is a bit orangey. So you can think that they're the same color, but it's not. They will all have their own frequency. Okay, so this is the emission spectrum. Okay, you get the idea? Yes. Alright. Thank you. Okay, so grade 12. Now here they ask questions, do the frequency, do the time for each different waves. We're not going to do this now because this is child games. But you just need to know you will need this formula also for this chapter because we work with frequency and we work with time and. Okay, another formula that you might need is this one. Okay, where the number of how many electrons did jump or whatever.
What is the word of the charge? It's a C.
Yes, so.
No, there.
So it's a Q over E. I just want to check if it's on your data sheet. I can't remember. It's not on your data sheet. This one. No, it is. This one is also on your data sheet. But just notice like this one is with sound and light. This one is with electrostatics. You saw? And then these formulas that we just did, well, these ones are also with sound and light. Okay, so don't think you have to stick with one table. You can go to another table if it is appropriate. All right, now you can see there's lots of practice here with the answers. So let's not waste time with this. You can go through this, but I want to go to past papers here. Okay. No, my page is different from yours. It's the last chapter in your notes, the last question. Question 20. Okay, now let's see the English one. Where is the English book? Did someone take my English book?
76. 76.
Did someone borrow? Wait a second. Never mind. Okay. It says a light is incident on a cathode of a photoelectric cell connected to a battery and a sensitive ammeter. The cathode has a work function, so there you get the work function. Light of frequency so much is shown onto the cathode. Okay, so there you get the scenario, you see the battery, blah, 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 blah. What conclusive evidence about the nature of light is provided by the photoelectric effect? What was this thing that they've discovered with the photoelectric effect? Light has? Say again? No. No, not the photoelectric effect. What thing came out of the photoelectric effect? It showed that light has? No! Light has wave and particle nature, properties. So what is shown by this cathode? That light consists of wave properties and particle properties. Light consists of made up of wave properties and particle properties. Wave properties and particle properties. define the term work function.
The minimum energy
The minimum energy required for electrons emitted from a metal surface. The minimum energy required for electrons to be emitted from a metal's surface. Electrons to be emitted from a metal's surface. The minimum energy required for electrons to be emitted from a metal surface. Where are you guys? Did you finish writing?
Yeah, I didn't write the definition, I just
No, write down the definition. Why do you think I'm waiting? It's in your notes, people.
Yes.
But you must write it down, Fatima.
Okay.
At least once in your life. The minimum energy required for electrons to be emitted from a metal's surface. Then they ask there, for 4 marks, calculate the maximum energy of an electron ejected from the cathode. Now that is what we just did. Okay, so quickly on your own, do that. What do we have?
You want the energy function.
The work function was given 3.42 times 10 to the power negative 90.
Is it 10 or 20?
20, sorry.
That's 20.
Times 20 minus 19. I just want to check it with Afrikaans once. Yeah, remember now there was a mistake. It must be times 10. That must be times 10. Okay, the frequency, they say is 5.96 times 10 to the power 14. And they want the kinetic energy. Okay, go, 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 go. Nee, man.
Named App of the Year and Editor's Choice. Available on Windows, iPad, and Mac. Liquid Text goes beyond.
Okay, Wontley, what did you get? And the unit? Joules. Yes? This multiplied by this minus this. Now they ask you, 20.4, the ammeter registers a constant current, of 0.012 amperes. Calculate the minimum number of photons of light that strike the cathode in 10 seconds. 4 marks. So here they combine circuits with this. Okay. So they give us current, they give us time. somewhere at the back of your head, a formula must pop up. Q. If you go to circuits, there's a formula that says lowercase q is equal to I delta time. Okay? So if you have the current and if you have the time, then you can get the charge. What is that? It's the total charge that passes through. Okay? What was the question? The question was, calculate the minimum number of photons of light that strike the cathode in 10 seconds, period. So we would then have, that is the total charge of all the electrons. And they want what? How many electrons? So what are you going to do from there? Then you're going to go to this formula. Because then, if you have the total charge, where will you find the charge of an electron? It's a constant on your data sheet, then you'll get that. Quickly do that on your own. Remember, you write down a formula exactly like it is given on your data sheet. So if it's a lowercase q, then it's a lowercase q you write down. Even if you're used to a capital one. (1.6 times 10 to the power negative 19). 1.6 times 10 to the power negative 19. You want the number of, you don't want the charge. So if you put in the negative, your answer will be negative, then you just have to convert it to a positive. So you don't have to put in the negative there. You can. Okay, can I unfreeze?
At the end, after you get our answer, the like J or
All right, 7.5? Okay. Then they ask, now this is a good exam question. They ask the intensity of the incident light. So intensity, and I want you to write this down somewhere. Intensity is linked to the number of photons. Not the frequency, not frequency. To the number of photons, not frequency. So we're not increasing the energy, we're increasing the number of photons. Okay, so they say there, the intensity of the incident light is now increased. So it means more photons touch the metal surface, which means more electrons are being emitted. They're not emitted faster, just more. How will this change how will this change affect the reading on the ammeter? Choose from increase, decrease, or remains the same, and explain the answer. Okay. What? 20.5. I'm going to give my answer in a moment. Let me just go through the motions. We said intensity increase in intensity actually. Increase in intensity, increase the number of photons that reach metal surface, yes, with the correct frequency obviously. A high intensity or increase in intensity increases the number of photons that reach the metal surface. Yeah, I should. Right. Okay. Which means it increases the number of electrons emitted from the metal's surface. Okay. What is the ammeter measure again? The ammeter measures the current. And if we look at this formula, current is charge per time. I just rearranged that other formula that we just used. So if more electrons are emitted, it means more charges will pass through. Now they don't go 2, 2, 2 at a time, but 4, 4, 4 at a time, for instance. So more charges meaning a bigger current, meaning the ammeter reading will increase. So I'm going to say current is directly proportional to charges, and thus it will increase. Number of. Okay. Now I quickly wanted to, but want to show you a video. Frak, nee man. I think I'm going to try to play this like 2. No, maybe not 2. Maybe 1.7. Okay, so this guy just nicely shows
Hi, it's Mr. Anderson, and this is AP Physics Essentials Video 86. It's on emission and absorption spectra. If we were to take a gas like hydrogen and put it in a discharge chamber and shoot electrons out, it's going to give off light that looks like this. If we were to analyze that light, if we were to split it in a prism, it would look like this. So instead of being a rainbow of light, we're going to get these discrete...
So there you see, hydrogen is actually this and this and this color combined give you this. So they took that warm light, put it through a prism, a triangle, and it give off these 4 colors. Okay, and that is how they know that is hydrogen.
Units of light, or these discrete photons that are carrying discrete amounts of energy. And this was puzzling to scientists for a long time. We could also shine light through that discharge chamber, and parts of it would be absorbed. And so this would be the absorption spectra. So most of the light would make through, but...
Okay, so then they send it through cold gas, and then they get the absorption spectrum. Emission, absorption. For the same...
Some of it isn't going to make it through. And this puzzled scientists for a long time until Niels Bohr finally figured it out. And what's happening, if we look at hydrogen just in the first 2 energy levels, is that as the electron goes around the atom, as it jumps to a lower energy level, it's going to give off a photon of light. And for it to move up to that other energy or that higher energy level, it's going to have to absorb a photon. And so there are discrete colors of light that are required for it to jump up. And as it jumps down, it's going to release these discrete colors of light as well. If you hit it with other colors, it's not going to do anything. It doesn't have the right amount of energy. And so this is conservation of energy. Conservation of energy in an atom or in a nuclei, where it absorbs a photon, so we call that absorption. And so what does that mean? The amount of energy in the photon and the atom or nuclei before absorption is equal to the amount of energy inside the atom or nuclei after absorption. And the same thing applies with emission. And so as we give off that photon, energy is conserved. The amount of energy we had in the atom or the nuclei before is equal to both the photon and atom or nuclei after. Now this is really valuable in science because we can look at what's being given off, so we can look at the spectra of emissions from any kind of element or molecule, and it tells us what elements are going to be found inside it if we know what those energy levels are. And so if you know anything about visible light, it's all the colors of the spectrums. As we shine it in a prism, as it moves through the glass, different wavelengths of light are going to travel at different speeds, and so it's going to hit it with a yellow photon.
Yeah, I just want you to see this.
And so these atoms are being bombarded by different colors of photons, but it has to be the right color. Let's say it's the right purple color. What's going to happen? It's going to jump to a higher energy level. What happens is it falls down to that ground state, it's going to give off that same exact photon. So you can model this. This is a PhD simulation. What I'm going to do is take one hydrogen atom, put it in a discharge chamber. I'm going to use a cathode ray to hit it with an electron and watch what happens. It gets high energy, and as it falls back down, it gives off a certain color of photon. Now if I were to hit it with not just one electron, but a continuous stream of electrons, before it's able to fall down again, it's giving off different colors of...
Okay.